UCSD ECE 111, Lecture 4 and 5 Set 2, Modeling Abstraction. This time we will be talking about the gate level and switch level modeling. The gate level modeling is just a lower level abstraction than what we've seen earlier than the behavioral versus RTL. It's just like we are drawing a schematic, and it's just like, we are just focusing on the gates, the hardware level implementation, and this is kind of closer to the timing of the gates, so it's a little bit more exact. It takes more time to synthesize, but it's also much harder to write if you're just thinking about the abstraction. There are built-in gate primitives that we could use for this, and then these gate level models have to be provided for the synthesizer to synthesize it into ASIC or the FPGA, whichever one is going to be the end product of the gate level modeling. Without further ado, let's go through an example and see how this looks like step by step. Assume that I'm going to do a gate level description for a 2-to-1 multiplexer, which we've seen many times by now. And if we did the gate level description like you've seen in your digital design course, this is how it looks like. We have, two AND gate, and then, the selector is going to be selecting between one of these AND gates, and then the results are ORed. And we're just going to take this design, which has 4 gates, G1, G2, G3, and G4, and we're just going to define it exactly how would we define a schematic. We will have the wires that are connecting these internal selection, but we will be using the description of a NOT gate, then G2, G3, and then we also have the capability of devising, timing that goes with the gate, because we can do this in simulation purposes. And post-synthesis, it looks like, an optimized version for this. We can go even one level further and do switch level modeling, and here we just don't even go further than the gates. We could define transistors and switches, and this is typically cumbersome, takes a long time to simulate, and at this level you actually need a better knowledge of the physical and switch level implementation. The switch primitives are also provided in System Verilog. Here, let's see a few of them. We have PMOS, CMOS, and NMOS. You can even have resistance and capacitive nets, and you could work with all of them. And you could only do this for digital systems. The analog systems are not, really reflecting the transistor behavior that can be used, and this is, in just some cases, just to provide more details. It's not a commonly used case of Verilog. Here is just a waveform of the different levels of simulation and how this looks like. You could take a look at the details further. Let's just go through one switch level modeling. The ideal switch and the resistive switch, which basically is, if you have a resistance once you close the switch or not. And here are some of the switch primitives. I doubt we will be using any of them in this course. This is just for your information purposes. You could use these constructs if needed in anything that in terms of the design looks like. Here we're just going to design a simple switch using the NMOS and PMOS. This is the NMOS in terms of the logic level. We could define an NMOS, PMOS, and CMOS switch. Here is just NMOS, PMOS, and you could define a CMOS switch, which is basically a two-way you may have seen before. And these are the syntax that you could use for these type of switches. Now, we want to do a gate level description of a 2-to-1 multiplexer using the switch level modeling. And I assume you've seen this before. You could define this works in terms of the CMOS switch that is using the selector bits on the NMOS, and then also you could use it on the PMOS to select one of the two in these two circuits, and this is how the switch level modeling looks like. The next set, we will be seeing examples how this actually works in different abstraction levels.